Assalamu alaikum. My name is Hamna Zaheer and I am from BS Physics Semester 1. Today is my presentation and my topic is electron force microscopy. First of all, I'm explaining you introduction of electron force microscopy. Atomic force microscopy, in short AFM, is an advanced technique of studying properties of material at an atomic scale. The technique has displayed a big role in field of science like material science, molecular science, and solid state physics. It arises from the scanning tunneling microscopy, in short STM. STM was invented in 1982 by Binning and co-workers to investigate surface of conductivity materials. STM was limited to only conductive materials like metals and semiconductors. In order to study non-conductive materials, AFM was invented in 1986 by Binning. The group focused on studying the force between the tip and the sample in the contact mode rather than the tunneling current. Binning and his group incorporated a spring-like cantilever to hold the tip. The cantilever was made out of a thin gold foil with the diamond tip. The cantilever adjusts the tip to the sample surface. The experimental setup of the approach depicted in the review letter Binning et al. 1982. The cantilever is between the sample and the tip. It is fixed to a modulating piezo E. You can see the diagram of cantilever. You can see this diagram. And now, what is AFM? Atomic force microscopy, in short AFM, is one kind of scanning probe microscopy, in short SPM. SPM are designed to measure local properties such as height, friction, magnetism with the probe. To acquire an image, the SPM or raster scans to probe over a small area of the sample, measuring the local properties simultaneously. How does AFM work? AFM operates by measuring force between a probe and the sample. Normally, the probe is a short tip, which is a 36 UM tall pyramid with 15 to 40 nanometer and radius. Though the lateral AFM resolution is low 30 nanometer due to this convolution. The vertical resolution can be up to 0.1 nanometer. You can see this diagram. To acquire the image resolution, AFMs can generally measure the vertical and lateral deflection of the cantilever by using the cantilever. The optical lever operates by reflecting a laser beam of the cantilever. The reflected laser beam strikes a position segment photodetector consisting of 4-segment photodetector. The difference between the segment of photodetector of signals indicate the position of the laser spot on the detector and thus the angular deflection of the cantilever. Again, this is the diagram of cantilever. You can see this and this is cantilever, tip, laser, position sensitive detector. Piezo ceramics position the tip with high resolution. Piezoelectric ceramics are a class of material that expand or contact when in the presence of a voltage gradient. Piezoceramic make it possible to create three-dimensional positioning device of arbitrarily high precisions. In contact mode, AFMs use feedback to regulate the force on the sample. The AFM not only measure the force on the sample but also regulate it, allowing acquisitions of image at very low forces. The feedback loop consists of the tube scanner but control the height of the tip, the cantilever, and optical lever which measure the local height of the sample, and the feedback circuit that attempt to keep the cantilever deflection constant by adjusting the voltage applied to the scanner A. Well-constructed feedback loop is essential to microscope performance. This is a diagram of AFM image of the nanobelt. What is contact and non-contact modes? There are two primary modes of operation for atomic force microscope: contact mode and non-contact mode. First of all, contact mode. Contact mode, the cantilever drags across the sample surface and it uses the deflection of the cantilever to measure the contour of the surface. To eliminate the noise and drift that can affect a static signal, low stiffness cantilever are used, but this allows strong attractive forces to pull the tip to surface. To eliminate this attraction, the tip is in contact with the surface is repulsive. And now non-contact mode. Non-contact mode, the tip vibrates slightly above its resonance frequency and don't contact the surface of the sample. Any long-range forces like van der Waals forces decrease the resonant frequency of cantilever. A feedback loop system helps to maintain the oscillation amplitude constant by changing the distance from the tip to the sample. Recording the distance between the tip and the sample at each point allows the software to construct the topographic image of the sample's surface. Most samples will form a layer of moisture on the surface if stored at ambient condition, and this can make it difficult to measure the sample accurately. If the probe tip is close enough to detect the short range forces, then it is enough to stick the moisture. One way around this is tapping or dynamic contact mode. And now tapping mode. In tapping mode, cantilever uses a piezoelectrical element mounted on the top to oscillate it at near to its resonance frequency with an amplitude up to 200 nanometer. The force causes the amplitude decreases as the tip gets close to the surface, and the height of the cantilever adjusts to keep the amplitude constant. This tapping results in less damage to the sample than contact mode and is more accurate than non-contact mode when moisture is present on a sample. And now, advantages of AFM. AFM is a powerful tool that is invaluable if you want to measure incredibly small samples with a great degree of accuracy. Unlike rival technologies, it does not require either a vacuum or ghee sample to undergo treatment that might damage it. At the limits of operation, however, researchers have demonstrated atomic resolution in high vacuum and even liquid environment. Disadvantages of AFM. One of the major downsides in the single scan image size, which is of the order of 150 to 150 micrometers compared with millimeters for SEM. Another disadvantage is relatively slow scan time, which can lead to thermal drift on the sample. As the technology measures, researchers are relying on the being progress instrumentally, requiring improved signal to noise ratio, decreased thermal drift, and better detection and control of tip sample forces, including the use of sharp probes. And now the testing method of AFM. AFM of human hair cuticles, a microscopic study of environmental effect on hair morphology. We have used an AFM to provide quantitative real-time analysis of human hair morphologic changes under ambient conditions. This form of microscopy combines the lateral resolution of an electron microscope and the flexibility of a light microscope. 3 experiments were performed: a study of hair morphology in air versus water, a kinetic study of hair hydration, and a determination how pH changes pH changes affect hair morphology. The overlapping keratinized cells that form the hair cuticle spread out of 50 to 150% when hydrated, compared to a total shaft diameter changes of 10%. This hydration reaches a point with the first few meters after immersion. Also, hair swells much more at higher pH. Now you can see diagram. Second method is nanoscale mapping of mechanical and chemical surface properties of pigment coated surface by torsional harmonic AFM. In this study, torsional harmonic AFM was applied for surface mapping of the mechanical properties of pigment latex coated paper samples. In addition, topographic images and forces map of adhesive tip sample interactions were captured concurrently. The spatial distribution of latex binder on the composite surface was distinct between high resolution. The latex was found to dominate the surface chemistry of the composite coating, despite the fact that latex is a minor component the coating color formulation. The latex resides as a thick layer between the pigment and as a thin layer on an individual pigment. In addition, the tip sample thermodynamic work of adhesion of the composite material on the coated surface was compared to the surface energy values obtained by contact angle measurement. A high tip sample work of adhesion correlated to high surface energy. And the third method is tensile test of a single nanofiber using on AFM. In this study, an approach of electron force microscopy tipped to stretch a single electrospun polyethylene oxide PEO nanofiber is demonstrated. One end of the nanofiber is attached to a movable optical stage and another of the nanofiber is attached to a piezoresistive AFM cantilever. The nanofiber is stretched by moving the microscope stage and the force is measured via the deflection of cantilever. The elastic modulus of PEO nanofiber is found to be about 45 MPa. Thank you so much. This is my presentation.